Yes, sir.
Where do you get the 9 from?
Completing the square. Half of b, this is b, 6 is b. Half of b is 3. Squared is 9. Review. We just did this. Maybe not quite this elaborate, but we just did these types of problems with going from exponential to logarithmic or logarithmic to exponential form. There are a couple ways to do this. I will show you the, if you forget the shortcut, longer way first. So the first thing I want to do, so chapter 10, today we're going to do kind of like all the ideas of chapter 10. I'm going to work through some example problems in chapter 10, but there are not any check your understanding problems out of the book that I necessarily am going to assign you to do so that you know what's going on. So it'll be looking at the examples we did, reworking the examples probably a few times, in preparation for the final exam. For those of you that are taking pre-calc next, you will spend a lot more time on this in pre-calc. If you're taking stats next, you will probably never see this again. So put that in that category as you're thinking through what's going on. So long time ago, someone decided to think, well, what would happen if I took a line like, let's move this out of the way for a second. Move that up there. So if I took a line like this, and then I took a single point right here, and then what happens if I spun that line around, but not like a spinner like you would see on a like a game that you might play, a board game, not a spinner, spin it around like that, but spin it three-dimensionally so that it would rotate around. This would rotate around, and it would make this three-dimensional double cone revolved around this point. So this is kind of how it started, again, long time ago. And then they said, well, now, what if we slice it? So now think of if you've ever been to the deli where they freshly slice your meat for you. And if you had a chunk of meat that was in this double inverted cone, what would your meat slice look like if you sliced it completely straight across? Well, that would be a circle. What if I sliced it parallel to this line, but not on that line? So like right here or right there, or like that's what this one is showing. And if I move up here and do this upper one, what would that look like? That's in the shape of a parabola. All right. Or a third way is what if I do it instead of straight across, right? So when I say straight across, I'm talking parallel to the base, but I do it just at a little bit of an angle. You probably called it an oval, but its official name is an ellipse. And then the fourth is what if I am parallel if you do it vertically so that it would be parallel to this line of symmetry that goes up, you would get a shape called a hyperbola. So these four shapes are what are referred to as conic sections. All right, and conic sections, so that's what we're going to be talking about today, are the conic sections, and there's 4 of them. We will start with the parabola because we've been there recently. Then I think we're going to do circle, ellipse, and hyperbola. And I'll talk about, people usually say, so why are these studied? What is the big deal about these 4 things? Aside from circles, ellipses, and parabolas, they occur many different ways very naturally, and we actually use them in manufacturing processes for a variety of things because of some of their unique characteristics. All right, but we're going to start with the parabola, which we've done this. We've looked at this in the past, but when I did it, it was, let's see, when we looked at it the other day, we had it written as y equals a times, oh, no, we didn't write it like that. We did y minus k equals a times x minus h. All right, because the last time we got together, we actually were doing completing the square to find the vertex. All right, these are the same thing. They're just written slightly differently. All right. This 4p, if I moved it over here, it would be 1 over 4p. All right, if I divided both sides by 4p. And that's the a value. A is equal to 1 over 4p. But we'll get to that in a second. So the vertex of this is h comma k. In a parabola, I do it like this. If I do a generic parabola, let's say this is my vertex. There's my parabola. A parabola has a line, and again, this would fall into the category of, if you're taking pre-calc next, you're going to spend more time on this. If you're not, you can ignore this next little part, but it just gives an understanding for what's going on. We have a line right down here. If you can almost see those dots. Okay, I shouldn't have tried to repeat all those dots. It's harder to see. I'll just kind of make it a line, but I'll do it in red. So this line down here is what's called the directrix. That's an I. A directrix. How a parabola is constructed is inside of a parabola, there is a point called the foci. Or there's only one, so it's called the focus. Every point on my parabola, so if I take this point right here, it would be the same distance from the focus as it is from the, oop, that's a terrible, should go straight up and down. All right, those blue aren't showing. Dot, 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 dot. So if I could draw this accurately, the distance from the focus to that point is the same distance as that point is to the directrix. Now you might look at this and say, well, it obviously is not. Well, that's because I didn't draw my parabola really well. But in terms of how a parabola is defined, a parabola is defined as the set of points that are the same distance from the focus as they are from the directrix. All right, so if I actually, yeah. So this point, the vertex, this distance here is the same as this distance there. All right, and that's how a parabola is supposed to be drawn. Mine is not super great, just because, again, I'm just sketching it. But that's the idea of what a parabola is, and that 4p is related to this directrix line. All right. But what we're going to focus on for our class primarily is finding the vertex and the importance of then what that vertex is. Now, in life, we'll do a bigger thing like this. All right. The application of what the focus is in a parabola. So if I to go back here, there we go. If I were to make this nice, big, and yellow, if that were a thing that emits light, or something that emits any kind of a wave, sound wave, light wave, something like that. If I took that, and if any light source that comes from that hits the parabola, it will be reflected out perpendicular to the directrix down here. All right? So anything perpendicular to the directrix goes straight up, but anything that comes and would hit that parabola gets reflected out that way. And it doesn't matter which direction, so if I do it over this way, I'll do blue as a different color. Burnt, burnt. If it would hit right there, it would reflect in that direction. Down here, it would hit and would reflect perpendicular to the directrix, so that all of these reflections are all going to be going in the same direction. This is the principle, this is the same idea as how headlights are formed. A headlight will have a shape like this. It's parabolic. At the focus of that parabola is where they actually install the light bulb. So that way, any light that goes back this way gets reflected straight back out of that light. Even, you might even think like over here, it's going to like reflect to this spot here, and it's also going to go out that way. Now you can't have, well, the deeper that this parabola is, the more of the light gets focused out in this direction. All right, they actually make flashlights now where you can, twist the end of the flashlight to make it quote unquote brighter. What you're actually doing is you're deepening how much of the parabola is being exposed to the light so that it focuses more of the light downstream. All right, so there's a practical application of what a parabola is used for. Back to my focus. But what we're going to do is we are going to find the vertex. And you might look at this and say, wow, it looks a little bit different than we had before, which is true. So what we're going to start with is we're going to move the y's to the left. So I'm going to have on the left-hand side 6y plus 3 equals x squared minus 8x. So procedurally, it was the same as what we did before. I want this coefficient to be 1, which it is. All right, but over here we'll have 6y plus 3, and we'll deal with that later. But right now we're going to complete the square on this side. And that process of completing the square is I take a half of b and I square it. So what I'm taking is I'm taking half of -4 and then squaring that. And half of -4 is -2. Squared is 4. So I'm going to add 4 over here, and I'm going to add 4 over here. And the advantage I have using different colors is you can see I did the exact same thing to both sides to set that up. So on the left-hand side, that simplifies to 6y plus 7. On the right-hand side, I'm going to then factor this. X minus 2, x minus 2. Two numbers that multiply to positive 4, that add to -8. Ooh, that's not right. Half of 4, yeah, see?
Where'd you get 4?
Yeah, that's a good question. So I messed this up. This is, it is -4. Or B is -8. That's what I did. I halved it and then I halved it again. So, my apologies on that. That should be erasing. Erase this. Erase this. We'll erase this. And this here. All right. B is -8. So that's -8. I take half of b is negative 4. And negative 4 squared is 16. Yeah, so what I did accidentally is I took half of b and put it there, and then I took half of it again. So I tried to do this step twice in a row. That's where my mistake came. And I realized it as soon as I had to factor. I was like, wait, that's not right. So again, take b. b is negative 8. Put it right there for b. Negative 8 times a half is negative 4. So this in here is negative 4 squared. Negative 4 times negative 4 is positive 16. So I'm going to add 16 to both sides. Which means this is not 7. 16 plus 3 is 19. On the right-hand side, now I'm going to look to find out, is there a way that I can factor this such that I have two numbers that multiply to positive 16 that add to negative 8? Negative 4, negative 4. This number should be what I had inside this parentheses. Half of b, half of negative 8 is negative 4. It should be negative 4 and negative 4. And the reason why I want that is I want x minus 4 squared. This equals 6y plus 19. The next thing I need to do is I need to take this number. I want this now to be a 1. In order for the coefficient of the y to be a 1, I have to divide it by 6. I have to divide this by 6, and I have to divide this whole thing over here by 6. When I do that, I will get y plus 19/6 equals, I'm going to rewrite the division as multiplication. This is dividing by 6, so it's just same as times 1/6. Now I have it in standard form. What that allows me to do is then say, all right, well, what is the vertex? The vertex is, when I'm looking at this, and I can rewrite the equation if I want, y minus k equals a times x minus h squared. Is this already minus, just like the standard form is minus? Yes. So this is my h. This is my h. And what the h is the x coordinate of the vertex. The other way to think about it, which I said in class, was what makes this 0? 4. 4 minus 4 is 0. So for the vertex, the x coordinate of the vertex is 4. I look over here. Is this minus? No, it's not. So whatever k is will be the opposite sign of this. Or, in other words, what makes this 0? What number could I put in for y that makes this 0? Negative 19/6, and that's the y component of the vertex. All right. The a is a number less than 1. It's 1/6. That simply means that when I do my graph of my parabola, it's going to be wider. It's going to, if I were to graph this, let's see, 4 over negative 19/6 down, something like that. Instead of it being a parabola that's like down and up like this, it's going to be actually much wider. So what do I mean by wider? I mean that it will be more of a flat saucer than, say, a cup. All right, the 1/6 means it's going to be spread out more. if this number were greater than 1, if I had a number like 2, it'd be much steeper. So much like slope, a slope of a line, if the higher the slope is, the faster it goes up. It's the same thing with a parabola. This is kind of like the slope. Not exactly, but similar. So if it's a smaller number, closer to 0, it'll be a much flatter parabola. All right? But as we think of all of this, the big idea that we're hitting on is, if given this, how do I find the vertex? All right? And we're going to be talking about this later as we go through all the different conic sections. We also look at this and say, how do I know it's a parabola just by looking at it? All right? And there are ways to tell it. For example, in this one, I look at this right away and I know it's a parabola because only one of them is squared. The x is squared. The y is a regular y. It's not squared, which means if one of them is squared and the other one is not, it will be a parabola. All right? If the x was not squared and the y was squared, it still is going to be a parabola, but it's going to be a horizontal one. We will not be doing any of those. Right? If I have something like this, that meant the equation had x's and the y would have been squared. All right? Again, if you're taking pre-calc, you'll spend some time with this, but we will not do any more with that. We are only focusing on just a regular where the y is power of 1 and x is squared. And that's why I know, oh, this is a parabola. Means I'm going to move my y over there, my solid number there, going to complete the square on the x and work my way down. All right? Here is a circle. With a circle, here's the standardized version of what a circle looks like. On this, the vertex, and a vertex of a circle, we don't call it a vertex. We call it the center of the circle. Last one's for a parabola, yep. The center of a circle will be h comma k. It's going to follow the same format for the letters we choose. And r is the radius. All right. So if I had circle x squared plus y squared equals 25, this is a circle. If you try to graph this, you would get a circle. The center would be at 0, 0. How do I know? Well, if I go x minus 0, that's just x. So it'd be x squared. Y minus 0 would be just y, so it'd be squared, equals 25. So I would have a circle. One, two, three, four, five. If I can make those equal increments. Like that. So this is negative 5 right there. Right there is negative 5. This is 5. This over there is 5. And the radius is 5 because r squared is 25. So square root of 25 is 5. So that's what a circle would look like here. All right, and this would be like a very, very, very easy, quote unquote, easier circle to identify. How do I know it's a circle? Because the y squared and the x squared, well, the highest power is squared for both, and I'm adding them together. And there's going to be another element that we'll get to when we talk about an ellipse, but we'll get to that in a minute. All right? Well, here it is. The coefficient of the x and the coefficient of the y are the same. If they're different, then it's not a circle. And that'll be an ellipse, and we'll do that when we get to ellipses, which I think is after we do circles. But what we're going to do is look at an example of one right now. So here, I know that this will be a circle because the x squared and the y squared have the same coefficient. They're both 1. All right. But we need to find the center of the circle. So what I'm going to do is I'm going to first treat this like we did before with a parabola, and I'm going to complete the square on that part only. So I'm going to take half of b, so half of negative 2, and I'm going to square it. Half of negative 2 is negative 1. Squared is 1. So on the left, I'll have x squared minus 2x plus 1. Now that 1 that I added here, I have to add over there, so I'm going to have plus 1 over here. So that way I still have equal things on both sides. On the left side, I still have x squared minus 2x, but I added a 1 to it. Since I added a 1 over here on that side of the scale, right, my balance point is my equal sign, had to add a 1 on the right-hand side as well. Then I am going to do this just like I did parabolas, and I'm going to complete the square for that one. So I'm going to take half of b and square it. So half of 6 is 3. Then we're going to square it. And that will be 9. So I'll have this plus comes down, plus y squared plus 6y plus 9. And I got to do a plus 9 up here. So 6 plus 1 is 7. 7 plus 9 is 16. Now, over there in yellow, I'm going to say, can I factor that? That's a, ooh, come on, don't move it like that. There we go. That's a trinomial. Can I factor this? If I've done my completing the square correctly, the answer is yes, I can. Two numbers that multiply to positive 1 that add to negative 2. Negative 1 and negative 1. Which also is that number. Half of b, if I did this the right way, will be the same number that these are. And then that will be x minus 1 squared. Anything times itself is squared. I'm going to do the same thing with my y's. Can I factor that? Two numbers that multiply to 9, that add to 6. So this will be plus y plus 3 squared equals 16. X minus h squared plus y minus k squared equals r squared. This we had on the last slide. That's the general form, or the standard form. This is standard form for a circle. I now have it in the standard form for a circle. The center of my circle will be at the point that makes this 0. So my x value will be 1. And my y coordinate will be the number that makes this 0. So y would have to be negative 3. Because negative 3 plus 3 is 0. Over here, 1 minus 1 is 0. So my center is this. And then my radius this 16 is r squared. So just r is 4. Oh, didn't get everything. Let's go like that. There we go. Move all that over. Move that over. So then if I had to graph this, 1 over 3 down, so I'm going to be in the last quadrant. 3 down, 2, 3. That's the center. The radius is 4, so it'll be up 4 to that point. 1, 2, 3, 4 over there. 1, 2, 3, 4 over there. 1, 2, 3, 4 down, about like that. So again, procedurally, I know it's a circle because the x is squared, the y is also squared. They're either both positive, which these are, or both negative. And the biggest thing, the coefficient of the x squared and the coefficient of the y squared are the same number. If they are the same number, then it will be a circle. If they're different numbers, we'll do an ellipse, which is the next slide up. Over. So now an ellipse. There is the standard form for an ellipse. In an ellipse, the a squared and the b squared will tell me if it's going to be, basically, if I graph it and it's an ellipse like this, that meant the larger value was under the y, because it's a vertical one. If I graph an ellipse and it's like this, that should be symmetric, not potato-shaped. But if I have a horizontal one, that meant the larger of these two numbers was under the x. But for our sake, I'm going to look at this and say, at a glance, I look at this and I know this will be an ellipse. The reason why I know, aside from the fact that that's what we're talking about, and naturally you're like, well, of course it's going to be ellipse, because he just showed us the ellipse formula. Both of them are squared. The highest power, it's both of them are squared, the x squared and the y squared. They're either both positive or both negative. In this case, they're both positive. But the coefficient of the x is 1. The coefficient of the y is 4. This being the case here means that this will be an ellipse because they have different coefficients. But procedurally, we are going to do the same process. Let's look at this first. Half of b, so half of 2, squared. Half of 2 is 1. 1 squared is 1. So I'll have x squared plus 2x plus 1. On the right-hand side, I'm going to add 1, because I added 1 over here. Everything else on the left-hand side, x squared plus 2x, was already there. Adding the 1 was the one change. That goes over there. To do this, before I can do completing the square, I need the first value. I need that y squared. I need the coefficient to be 1. In order to do that, I need to factor a 4 out of it. So I factored a 4 out of both of those that have a y term. And then I'm going to leave this as plus something for right now. To do, now I can do completing the square. So the first thing I had to do before I could, so in an ellipse, coefficients are different. That's a 4, that's a 1. I have to factor the 4 from both of my y terms out in front. Now I can do completing the square. Completing the square, I have to have a first coefficient of 1. So now this is my b. So I'm going to do it up here, just so I have some space down below. I'm going to take half of negative 6. I'm going to square that. So half of negative 6 is negative 3. Negative 3 squared is 9. Now be careful here. An instinct would be to write over here plus 9, but that would be wrong. And here's why. I have all of this inside here being multiplied by 4. So what I really added to the original equation was I added 36. And if you're wondering, what is he talking about? Yep. Up here, I'm going to move everything down here for a second. If I had 4y minus 24y plus 36, that's a terrible 6, plus 36. If I had this up here and then I factored a 4 out of each of them, I would have 4 parenthesis, that's supposed to be a y squared, I'd have 4y squared, so that'd be 4 and then y squared. Factor a 4 out of negative 24, that's negative 6. Factor a 4 out of 36, that's plus 9. So I had to do the completing the square inside the parentheses, but this 9 added to the left side of the equal sign had to be multiplied by 4, which is why it's a 36 on the right. So then I have plus 4 parenthesis y squared minus 6y plus 9 equals, let's see, 33 and 36 is 69, 70. Next up, now we factor. X plus 1 squared plus 4 times y minus 3 squared. Again, I skipped a little step in there, but we're thinking what two numbers multiply to 9, positive 9, that add to negative 6, negative 3 and negative 3, so it would have been y minus 3, y minus 3, but that's y minus 3 squared. On the right-hand side equals 70. I am almost to what it would look like for standard form. All right, as someone just pointed out, this was a negative 33. So negative 33 plus 1 plus 36. I accidentally did positive 33. So this is not 70. It should be, what number? Positive 4. So now, again, I'm almost done. And down here at the bottom, I'll rewrite what the standardized form was again. It was y minus k squared over a squared plus x minus h squared over b squared equals 1. It will always be equal to 1 when I write it in standard form for a hyperbola. For an ellipse, I mean. Also for a hyperbola. But this is an ellipse. So I need to find, how do I make this 4 into a 1? If I divide everything up here by 4, my final version will be x plus 1 squared over 4 plus y minus 3 squared over 1 equals 1. All right. Now, you might be looking to say, well, this is the y and this is x. You can have it, again, because it's adding, I could have this whole thing if I wanted to. I could just like, oh, just let me just select this. Come on. Nope. Thought maybe it would allow me to, no, just select that one part. I could take this and rewrite it as this plus this value, or this one there. So these are, even though that looks like they're in different formats, they're in the same format. What do I do next? I don't know why the plus didn't want to move. Come on. There we go. The center of my ellipse is at, what makes this 0? -1. What makes this 0? +3. What is my a? The value under the x is 4. And that would be something squared, b squared, which means in this case my b is 2. My a, the value under the y, is a squared. Well, if a squared is 1, then a was also 1. And then to graph it, at -1, 3, so if I go like this, -1 up 3, 1, 2, 3, that's the center of my ellipse. The b, or in this case, that's under my x, is 2. So from this point, I am going to go 2 in the x direction. Again, this number under the x squared portion is the x direction from the center. So from here, I'm going to go to the right 2. 1, 2. I'm going to go to the left 2. 1, 2. In the y direction, the value under the y component is 1, which is a squared. Square root of 1 is 1. So I'm going to go 1 in the y direction. So I go up 1. Oop, put my dot there. Up 1. I go down 1. And now if I can, sort of, that is how you would draw the ellipse. All right, my oval. So the center is still the center, like it was in a circle. The direction in the x direction will be the square root of the number under the x component. How far I draw it in the y direction will be the square root of what's under the y component, which is why when I did the last slide, I said, whichever is larger tells you if this is a horizontal. So if the larger value is under the x, it's a horizontal because it's going to go in the x direction. If the larger number were under the y, it would be a larger number up here, so it would be a vertical oval. So in order to be in standard form, this has to be a 1. It was a 4 here in red. So we factored this green thing into x minus 3. This has to be 1. In order to make that a 1, I would divide it by 4. I divided this whole thing by 4 and this whole thing by 4. Because this is trapped by the squared, there's no reducing possible with anything here, so it stays x minus 1 squared over 4. Here, this is all trapped inside the squared, y minus 3 squared, so it cannot do any reducing, but this 4 is outside of the parentheses, and it's 4 times, and as long as we're only multiplying and dividing, 4 times this giant thing, I can reduce this 4 and this 4. Leaving me with 1 in the denominator there. Before I get to a hyperbola, if I have an ellipse, the center would be right here. An ellipse has 2 foci, right there, or 2 focuses. So a parabola has 1 focus, an ellipse has 2 focus, or we call them foci. All right. Again, if you're taking pre-calc, you'll go into how to find those values. We're not going to spend that time in this class, But, fun fact, just like we did in the last one, any wave that's emitted from one of them hits the edge of the ellipse, it reflects back exactly to the other focus. And it doesn't matter where. If it goes like this, it's going to hit there. It will, oh, that's terrible. It reflects back to the other focus. Two things about this. Has anybody ever been to Washington, D.C.? If you do, go to a place called the Statuary Hall. If you get a tour of the Capitol, you go to a room called the Statuary Hall. It's now called the Statuary Hall because it's lined with statues of a lot of presidents. All right? But in the Statuary Hall, it is an ellipse. And they actually will do this if you're on the tour. This actually used to be, the Statuary Hall used to be where Congress met. Before they had their own building, they would get in there, let's say it's Democrats or Republicans or whatever your parties are. They would meet down here, the other group would meet over here, and they would discuss and argue about certain things, would come to the middle for the debate. The fun fact is if you sat exactly on this focus and you just listened, even in the midst of all the ruckus noise, everybody talking and arguing and debating, whoever was right here, even if they were whispering in a room full and crowded full of people, if you were sitting right here, you could hear what they were saying over the noise of everything else going on, because every sound they made reflected exactly back to you at that spot. And they're actually, and I don't know if it's actually true or not, but there's this story that one of our founding fathers put his desk right there. And he sat there with his head down most of the time, because all he was doing was eavesdropping on what the other party was trying to discuss and debate. So then when they'd come together for these discussions in the middle, he already knew what their argument was, and he had already come up with his rebuttal to what they were saying. All right, but if you ever go to D.C., go to Statuary Hall, you'll sit right here, and then your tour guide usually goes over to the other spot, and then they'll basically just say something in regular voice that if you're standing right there, you can hear it. But if you're just outside of it, like the rest of your tour group is they don't hear it, it's because they're just outside of that focus. And it doesn't take much of a difference, and then they're not going to hear what's being said. Another one, this was my uncle. My uncle produces massive kidney stones. If you've ever had one or know someone who's had one, they are extraordinarily painful. But you would sit in a tub that's elliptical shaped. There would be a chair right here, and it's filled with water, and you would sit in this chair. And they would get your kidney stone right at that one focus. They'd adjust your body and boom, okay, don't move. At this focus, they would have a speaker with a very low frequency sound wave, and those sound waves would go out and reflect back. Out and reflect back. And you all know this, if you ever hear someone with a big bass, you can literally feel it in your soft tissue. That's what would happen. It would go through the soft tissue, hit the kidney stone. All those vibrations would actually then cause the stone to shatter. And again, big bass competitions, the winners usually are the guys, usually guys, maybe women too, who end up blowing out their own windows. Right? Because those low frequency sound waves, when in just the right frequency of them, can actually crush solid stuff. So that's what they would do. And then you would break up those stones to small enough pieces that you could eventually pass them, aka pee them out. Also painful. Hyperbola. What's the difference now? It's minus. If one of them is minus, either the x squared or the y squared, it'll be a hyperbola. And if one of them is negative, that'll be whether or not it's going to be a vertical hyperbola where one goes up and one goes down, if you remember back to the original shape, or horizontal if it goes like this and like this. But our biggest fact is we just want to work on how do we find the center of the hyperbola. Guess what? Completing the square. So here we are again. I look at this, and at glance I go, aha, this will be a hyperbola because they're both y squared and x squared. They are different coefficients, which actually doesn't matter in a hyperbola. What matters in a hyperbola is one of them is negative. The other one is positive. So for a circle and an ellipse, they're both positive or both negative. For a circle, the value in front of the y squared is the same as the x squared. For an ellipse, they're both positive or both negative, and the value in front of the x squared and the y squared is different. Now, we have an x squared and a y squared. One is positive and the other one's negative. This will be a hyperbola. And we start by doing the same thing. Let's look at this. I need to first factor the 4 out of them. Y squared minus 4y plus something. I'll have negative 1 times x squared plus, oh, I need to do something first. I'm going to take this 1, I'm going to move it over there. Because all I want are x's and y's on the left. I want my numbers on the right-hand side. So it'll be equal 1. Adding 1, put it over there. So x squared plus 2x plus something. Once I have these first coefficients of the x squared and y, once they're a positive 1, then I can do completing the square. I take half of negative 4, and I'm going to square that. So half of the middle term. Half of negative 4 is negative 2. Negative 2 squared is positive 4. And if I added 4 over here, I have to add something on this side, but I'm not adding 4. I'm adding 4 times, so this 4 is being multiplied by 4. So I'm adding 16 on the right-hand side. I bumped part of the screen with my hand. There we go. Then, on the x one, I take half of 2, square that whole thing. So again, the middle term is 2. Half of 2 is 1. 1 squared is 1. But I'm not adding 1 to this side. I'm adding 1 times negative 1. I'm actually subtracting 1 from that side. So now, on the left, I'll have 4, parenthesis, y minus 2 squared. This factors into y minus 2 times y minus 2, which is y minus 2 squared, minus x plus 1 squared equals 16. So then I'm going to remember that the y minus h, or k, squared over a squared, x minus h squared over b squared equals 1. That's the standard form for a hyperbola. So then I look at this equation and say, what do I need to do to get it to look like that? I need to divide by 16. Because I need it to equal 1. So my final equation will be, let's see, 4 over 16. I'll have y minus 2 squared over 4 minus x plus 1 squared over 16 equals 1. The center of that hyperbola will be at the point -1, comma 2. I got 2 in parentheses there. Because I'm looking, what makes the x net, what makes this 0? -1 for the x's. What makes this 0? +2 for the y values. All right. And then the 16 and the 4 are going to be part of how you will graph it when you take pre-calculus. And which one's positive and which one is negative also goes into whether or not it's a vertical. So when I say vertical, I mean if I graphed a hyperbola, it would look like this and like this. It almost looks like 2 parabolas, but it's not. They're actually, I should probably do a better job. Hyperbola are actually wider and follow asymptotes. So there would be an asymptote that goes like this, that graph will go close to and then just keep following. And another one here. So that would be a vertical hyperbola. A horizontal one would be take that, rotate it 90 degrees so that it goes to the left and the right. Again, we're not doing that in this class, but that's where this is headed. All right, and there's fun stuff about hyperbolas and hyperbolic shapes. You've probably heard of things like hyperbolic chambers because they're based on principles of hyperbolas, much like other things are for ellipses and circles and parabolas. Ooh. Yes, sir?
So, for it to be a hyperbola, they both have to be negative?
No.
Or what?
To be a hyperbola, this one, if I multiplied x minus 1 squared out, it's a negative in front, so the x squared would have a negative term. If I multiplied this one out, I'd have y squared, and there's nothing here, which means the y squared will be positive. So the y squared is positive, the x squared is negative. That's what makes it a hyperbola. A hyperbola, these numbers could be the same, or they can be different. It doesn't matter. And if I wanted to, I could say, so,
Hyperbolas too.
oh, we haven't got to these yet. Yep. So, any follow-up questions here before I go to my next slide?